Okay, so I'm going to record lecture 16 on transformer. So transformer is currently the most important or the most dominating architecture for neural network. And it was first applied to natural language processing, in particular, machine translation. Then it was widely used very quickly in NLP, natural language processing, in multiple tasks with quite amazing results. After that, it also was adopted by computer vision so that it applied to image so that we have this vision transformer and transformer architectures that seek to replace the convolutional neural network. And it has also been applied to analyzing other data, for example, protein sequence or for protein folding and a lot of other applications. So it is a very important neural network architecture. It is based on the so-called self-attention, this attention mechanism. In fact, the original paper has a title called "Attention is all you need. You only need attention." But actually, from our perspective, we have been emphasizing the point of view that a neural network is a team of vectors, right? These vectors relay message to each other, pass on message to each other. For example, in convolutional neural network, you have vectors planted at on the image domain with at different layers, right? And those upper layers, those vectors at upper layers receive message from vectors, nearby vectors at lower layers. And in recurrent neural network, you have vectors at different time points, and then the hidden vector at one time point receive input from hidden vector at the previous time point, right? So you have those vectors, and these vectors can pass on message to each other. And here the transformer also is based on this point of view, probably push this point of view to the extreme in that, again, you have a team for vectors. So just like in a cocktail party, so these vectors pay attention to each other, talk to each other, communicate with each other, and collect information from each other. So this is almost like a thinking process, and it is so flexible, and indeed it can approximate different like a logical reasoning process implicitly. So let me again start from this translation, machine translation, to convey the basic idea, because that's the original application for transformer. So recall that in the LSTM transformer we studied in the last lecture. So we have the input, like I love machine learning. So each word is has a native representation as one hot vector. If you multiply the one hot vector by the encoding matrix, which consists of, say, 6,000 column vectors, one column vector for each word, right? You then get the initial embedding or initial vectors for those words. So each word become a embedding or a dense vector. Then you have a encoder, which is a box. We will open this box later on. So we have the encoder that encode the initial embedding into those final embedding. So here I use HM to denote the embedding of the mth word. And then you have the final embedding. Supposedly, it is like those vectors, they talk to each other, collect information or message from each other, like in a cocktail party, or maybe more formally within a meeting room, they talk to each other, and they may do this for multiple rounds for meetings. And then finally, those are the updated vectors. So it's just like in a meeting room, you have this capital M vectors, they talk to each other. And after several or maybe multiple, say 64 rounds, for example, you then get the final updated vectors. So those vectors, after talking to each other, actually become aware of other words in the same sentence. So each vector actually encodes the whole sentence in some sense from the perspective of this particular word. So at least those vectors are contextualized. So you pay attention to the context. And then you have this final layer of vectors after this process. So this is the encoding part. And for the decoding part, again, it is autoregressive. You start from this start symbol, start word, and then you go through this decoder. You do this one by one. You first generate the first word IMO, and you let IMO be the input to the next time step. And then you generate this machinist, and then let it to be the input to the next step. And then you generate the, and then aprendido, and then end of sentence. Until you generate end of sentence, you stop. So the decoder part is still like autoregressive model. You generate one word at a time sequentially, so that each word is generated based on the previous word. So therefore, again, you have at each time step, you generate a vector, right? Initial vector, which is the embedding of the previous word. And then you send this to the encoder. And then finally, you output a vector, which again contextualized you by paying attention, collecting information from the previous generated vectors, but also paying attention to the final layer of vectors, or the final updated vectors produced by the encoder, so that you get those vectors for different words in the input sentence by paying attention to those vectors. And then you generate this vector, and then you use a decoding matrix to decode this dense vector into the word by first calculating the logit scores for all the words, translate them into probabilities for all the words through this this softmax, right? And then you get the probabilities, and then you can generate the word either as a word with maximum probability or by sampling from the probability distribution over all the words. Okay, so that's the process. And so last time I did mention the training. In fact, the training is very similar to classification, because this is our input, this is given, and then this is output. So at each time we have this output probability, right? And then we have this classification. So each word is a category, and you classify into those, if you have 6,000 words, you have 6,000 categories. Then you have this probability of the observed category. So the idea is that you want to maximize the log likelihood, which is a log of the probability of the observed word at each time step. Okay, so this is autoregressive. So basically, you are computing the probability for, say, this word given the previous words as well as the input sentence. So you multiply all those probabilities and take a log for each input and output pair. So you get the loss function for each training example. And this log likelihood, if you take negative, it becomes so-called cross-entropy loss. And then you can you can minimize this loss function by stochastic gradient descent, where the gradient give you the error backpropagation. That is, for each word, you have this one hot vector, and then you look at the difference between this one hot vector and the corresponding predicted probability. So that will be your error, and then you backpropagate the error back to all the parameters in the decoder as well as the encoder, including the encoding matrix and the decoding matrix. So everything is learned so-called end-to-end. So from one end to input end to the output end, and everything is learned. All the parameters, including encoding matrix and decoding matrix, can be learned by minimizing the negative log likelihood. That is the log of the probability of the observed word given all the previous words and all those input sentence. So it's actually simple, because after all this calculation, you get the probabilities of all the predicted words, right? The probabilities of all the words, and then you look at what's the probability of the word that is actually observed. You want to maximize this probability. So that's the basic idea. So therefore, you know, the loss function and the backpropagation training is still essentially the same as classification. In the past homework, you actually you know, go over the equations, right, for deriving this top layer for this loss derivative in terms of one hot vector minus the probability vector. And then you also derive all those backpropagation steps. So that's essentially what powers the learning of this this type of encoder decoder type of transformer or machine translation system. And you can collect, say, hundreds of millions of pairs, say, of English sentence and the resulting translated Spanish sentence. So these are the pairs for the training data. You may have millions or hundreds of millions of pairs. And then you just use a batch, mini batch training, right? So you go through all those pairs and to do stochastic gradient descent. So that's the whole process of training. And in the past lecture, we considered LSTM structure. And we mentioned two shortcomings of LSTM. One is that the sequential nature make it hard to parallelize the computation. And more seriously, the sequential nature prevent a vector from collecting information directly from other vectors. It has to, the message has to pass in this sequential way. So this is quite a limiting factor. So therefore, in this paper, attention is all you need. Those authors, they developed this self-attention mechanism so that each vector can pay attention to any other vector and collect information and collect message in order to update itself. So that's the basic idea of this self-attention architecture. And in fact, the self-attention mechanism was used much before for both language and also vision, like image object recognition. So you have this self-attention, which is also in the form of softmax, although it is not for the purpose of classification. But the transformer paper further simplifies things. So it removes the LSTM sequential structure completely, only keep the self-attention so that the model is actually very simple and yet also very scalable. So you can use this simple architecture and build on top of each other to make it very big with multiple layers, just like a convolutional neural network, right? The basic operation is rather simple, but you can make it very big. You can make the size of the model very big if you want to learn from bigger data. So this simplicity and the scalability is a very good feature for any like a neural network or any method actually. So for this type of architecture, so as I mentioned before, it is really a like a team for vectors. So just to remind you about this vector representation or embedding, for example, I can be represented by a one-hot vector, right? If you have 6,000 words in your dictionary, then this is a 6,000 dimensional one-hot vector, depending on which word you observe. And then you embed it into a dense vector, meaning that each element is a continuous number, not necessarily zero. And this another word love, which is another one-hot vector, which can be embedded into another vector embedding. And as I mentioned, we don't need to read too deep into each dimension. So actually, the whole vector as a whole carry the meaning, and you can extract the meaning by operating on this vector. So this vector can be operated by a matrix, multiplying a learnable matrix to this vector to extract another vector. And you can decode the meaning of this vector by using some like a neural network, right? Like a multi-layer perceptron type of things. So this embedding is quite important because you can see that each word, so those words are discrete or symbolic, but you embed them as continuous vectors so that you can continue to apply like a neural network type of differentiable, learnable operations, right? So that's make it very flexible. And so this embedding, the idea of embedding is a key feature for neural network and deep learning. And we have been emphasized this point of view so that the neural network can be considered as a team of vectors that pass message to each other. And you can even do this for discrete structure, for example, a graph where you have multiple nodes connected through the edges. And then each node can be embedded as a vector, and those vectors can then communicate with each other, gather information from each other through the edges based on by multiplying the matrix to the vector to extract information. Okay. So the idea is that you can embed anything, either continuous or discrete, into a Euclidean space as a dense vector, or we just call this as embedding. And then you use neural network like a matrix vector multiplication to process those continuous vectors. And then you get the resulting vectors. And from the resulting vector, you can then predict the output. So that's the basic strategy for this embedding and the neural network as a team of vectors. But then as to this attention mechanism, so we have, for example, let's first look at the encoder, because the decoder is similar to the encoder with some extra elements to be added. So for the encoder, so the initial embedding, we have capital M vectors, right? And then each vector, say h small m, will pay attention to other vectors. Okay, so this attention, say this vector m, pay attention to other vectors. So the attention that this m pay to any other vector t, I use this a m paying attention to t, where t goes from 1 to t and to capital M, including itself. Okay, so that's, I put a circle here. So this m is our currently this pivot, or this, you can think of this as yourself or ego, right? This pivot vector, pivot vector. So it pay attention to all the other vectors. So I put a circle means that this is our viewpoint, or our standpoint view. So we, from the viewpoint of m, from this viewpoint of M, it pays attention to any other vectors. And this one is modeled as a softmax, but it's not really a probability for classification. Also, maybe you can also think of it that way, right? You pick one vector to pay attention. Although this is actually a probability, it's a probability over all the vectors, including itself. Okay, and it is softmax, so that it's exponential of a affinity score of HM, this pivot vector, to any other vector HT, and divided by the summation of exponential of this affinity score over all T prime from 1 to M. So here I use T prime just to avoid confusion, where we have this HT already. Okay, so this is a normalizing constant, like we use Z to denote this normalizing constant. So now you have this this A, this attention, which is sum to 1. So from the perspective of M, when M pays attention to all the other vectors, including self, so this attention should sum to 1. And as I mentioned, you can interpret this as a probability, but often we just interpret this as a weight, so that we can compute the weighted average. But you can also imagine, as I said before, so you just pick one vector to pay attention. Also here, it's actually just a smoothed. It's not one hot anymore, right? It's this is smoothed numbers that sum to 1. So maybe better to think of this A as a set of weights, and then you can compute the weighted average later on. Okay, so let's move to the next page. Okay, that's good. So I jump to this page very smoothly. And how do we define the affinity? So this affinity of this vector to other vectors. For example, in a cocktail party, you have different affinities to different people, right? So whether you like this person or not, so from this vector's perspective, whether this vector likes this vector or this vector or this vector, or how much this vector like this vector, this vector, and this vector. So this is based on this affinity, right? So how do we define this affinity? So it is defined, again, I circle this M. So this is from M's point of view. So this affinity of HM and HT is actually computed by a certain inner product between this query vector and the key vector. So here you have this H vector, right? And then you can extract a query vector by multiplying a matrix W, that's called W query, to this vector. So you get another vector, which may not be the same dimension as the H vector, maybe of a lower dimension than this H vector. And you can also multiply a weight matrix W key to get a key vector. And you multiply a value matrix W value to get this value vector. So the dimensionality of a query vector and key vector are the same, but the dimensionality of the value vector may be different. Okay, so you apply the same W query to all the vectors at this layer to extract query. So you apply the same W query to H1, you get Q1 vector. And to this HT, you get QT vector. Okay, so they all use the same shared W matrix. Similar to convolutional neural network, right? You share the weight matrix. And also the key matrix, W key, this weight matrix for key, for extracting the key from this H vector is also shared over all those vectors. And similar for this W matrix, to extract the value of the content of this vector from all the vectors. You use the same W matrix to extract the value vectors from all those vectors. Okay, so this is how we do that. And then our affinity is defined based on this inner product of query and the key. So the affinity of whether M, from M's perspective, whether M likes T or not, is based on this inner product between this query of M and the key for T. So query and the key, the inner product. If they have a big inner product, then this M lacks T. Actually, this inner product is also the way we use for like this recommender system. For example, you rent movies from Netflix, and then you may rate, give the movie a rating, or in general, customers or users may rate the items, right? So for each movie, you give each user may give a rating, but then of course a single user can only rate the movies that the user has seen, right? And also, each movie may only receive ratings from all those users who have seen this movie. So therefore, it's just if you look at these ratings, you only get partial ratings, right? So some users rate some movies, and then the rating is like affinity. So this affinity can be modeled as a vector for the user and a vector for the movie. So that is based on the existing observed ratings. So you can actually use a least square regression, least square fit, minimizing the least square loss. You can then compute a vector representation for each user, this Q vector for each user, and the key vector for each movie. So why do we do that? Because then for a movie that a user hasn't seen, you can use this product. After you compute the two vectors, you can use this product to predict what the potential rating this user may give to the movie, right? And then you can recommend those movies that potentially may receive high ratings from this user to this user. So that is this Q vector for the user is Netflix understanding of your personality. And in fact, Netflix may know your personality better than yourself. Sometimes, for example, we love something, we hate something, or we like something, we don't like something. It's just a feeling, right? We don't even know why we have such reaction ourselves. We are as puzzled as other people maybe. But by analyzing your behavior, and then the Netflix may figure out your cue, and also the Netflix knows the key vector of the movies. That's quite scary actually. So those big tech actually knows your personality better than yourself. Okay, so that's one just offline example. Now let's go back to this attention. So attention is based on the this softmax of affinity score, and this affinity score is computed by this inner product. And potentially, if you use higher dimensional vectors, then this inner product will be bigger, right? So rather you want to normalize it. So imagine that those Q and K are like the component elements are normal 0, 1 random variables, and then this inner product actually scale according to square root of dimension. So therefore, you want to divide this inner product by the square root of dimension as a matter of normalization, so that the affinity somehow is not does not depend on the dimensionality. Okay, so this is affinity, and after you compute this affinity based on this mechanism, where you extract those vectors using the matrices to be learned, and then you can compute the affinity, and from the affinity you can then compute this this attention based on using this softmax, just like here. So when you have the affinity based on this inner product affinity, and then you can use this softmax to decide how much attention I should pay to each t, so that the summation over all the t for this attention equals 1. Okay, so again, M is a pivot. From M standpoint view, M pays attention to all the other vectors, including itself, and this attention should sum to 1. Okay, and this is how we get this attention. And then we can decide how much we want to make a change. We use delta sub M to denote the update, very much like the update of the memory cells, right? So you decide this update, how much update, how much the change you want to make to this HM, this M's vector. And this is computed by collecting information or collecting the message or content from all the other vectors. But this is a weighted sum, so weighted average, where this from M standpoint view. So A pays attention to all the T, and then it collects the message from this VT. So it's a weighted average of VT. Each VT is extracted from this HT by this weight matrix W for value. Okay, and then you compute the weighted average of this VT, and this determines how much you want to change M. So if this is our delta M, and then we change HM by this HM plus, so you see this residual type of parameterization. So HM plus a matrix times this delta M. So delta M is the message you collected from all the other vectors, including yourself. And then you use this one, delta M, to determine how much you make the change. So this you have this residual parameterization. So this way, you see HM collects message or information from other vectors through this self-attention mechanism. So this whole thing is called self-attention. And then it helps to contextualize this vector, so that this vector collect information from the vectors for other words. Okay. Again, it is like in a cocktail party or in a meeting. You talk to people and you pay more attention. You talk to people, you gather their content or their message, but then you pay attention to those vectors that you like, or you are friendly with, or you trust. So this how much you trust or how much you care about this other vectors is determined by this scalar. This is the number of the weight. So it's a weighted average for all those value vectors extracted from all the vectors. Okay, and then you learn there's another learnable matrix that determines how much you change yourself. Okay, after you collect information from others, you change your knowledge or you change your thought. So this thought vector is updated based on the information it's collected from other vectors and weighted by how much this vector cares about the other vectors. So that's a basic idea. And after this contextualization, this collecting information, then each vector is like after the cocktail party or after the meeting, each vector goes home. And then this vector then think for itself, ruminating on the message collected from other vectors during the day or during the party or during the meeting. So that is, it goes through a, say, 2-layer or multiple layer. I think 2-layer is the standard 2-layer feed-forward neural network or multi-layer perceptron. So that is, you have this vector. This is actually a typical multi-layer perceptron. And then this is a hidden layer, which may be a bigger dimension for more flexibility. And then you have this vector of the same dimension as HM. And then you again update HM by HM plus delta M. So this delta M is different from this delta M. And this HM is different from this HM. So I'm just using this delta M to denote a further change in the second step. So the first step is you compute the change by collecting information from other vectors. And the second step is that you go home and you think for yourself. And then you decide how much further change you want to make. And then you add this delta m, this new vector delta m, which is different from this one to the current HM computed here. Okay, from here, you let this one to be the input to this feed-forward network. And then you get a new further change delta m. And you add this delta m to this HM. Again, it's a residual type of parameterization so that it is easy for backpropagation. And for each this addition, right? Each residual type of addition, this step and this step, after each one, you can also do a layer normalization. So that is for each, for all the HM, you just normalize the elements for HM to have mean 0 and standard deviation 1, just like a batch normalization, so that we can avoid covariate shift for more stable training and better result. So you have layer normalization after each residual parameterization. So there's a residual operation in step 1 and residual operation in step 2. And step 1 is done during the party by collecting information from others. And step 2 is done after you go back home to think for yourself, so that it doesn't involve any other vectors. Okay, so now, yeah, so this is illustration. So we have these vectors after this residual operation at delta m. So we do this normalization so that elements are normalized to have mean 0 and variance 1. Okay, so these are the two main steps. Okay, in each round for this self-attention. So let me go to the next page. Okay, so here is the overall architecture of the encoder. So for the encoder, we have the initial embedding, right? And then we have this self-attention, step 1, and then the residual operation, and then layer normalization. And then we go to step 2, feed-forward network, and then again, residual parameterization, and then layer normalization. So we keep doing this. For example, 8 or 6, for example, we do this 6 layers. So each layer has its own like those weights, right? The weight matrix for query and key and the value. So we have the each layer has its own set of weight matrices, and we have multiple layers, say capital N layers. And after, I just use multiply this by N. So after N layers, as a top layer, you have this multiple HM, multiple vectors. So now those vectors, they are fully contextualized by talking to each other, so that each vector actually encode the meaning of the whole sentence from the perspective of this particular word. And then you let the final layer of vectors to be the input for the decoder, so that you can decode the word in Spanish one by one. So that's the basic idea. And so before we talk about the decoder, maybe I need to mention two elements that we haven't covered. One is multi-head. So here we just use a so far we have talked about a single, like a weight matrix for query, a single weight matrix for key, a single weight matrix for value, so that for each vector HM, we have single query vector, a single key vector, a single value vector, right? But supposedly we can use multiple heads. We can use multiple heads. For the jth heads, each vector for the jth head, we use a W query J. So each head has its own weight matrix for query, weight matrix for key, and weight matrix for value. So each head has its own query vector, key vector, and value vector. Okay, so we use QM sub j to denote the query vector for HM extracted by the J's head. Okay, and this key vector for extracted from HM by the J's head, and the VMJ is a value vector extracted from HM by the J's head. And then we can actually use this attention mechanism. But here we need to compute this attention. So each head has its attention, and then we can compute this attention. Each head has its attention. So I add J here, denote the J's head. Okay, and then we each head compute the potential update delta M. So each head then using this operation by collecting the content or value of the J's head from other vectors, and then it decide how much it want to change. So imagine that in a cocktail party, so each guest, each person has say 3 heads, 1 to 3, and a person's head 1 talk to other people's heads 1, and a person's second head talk to other people's second head, and a person's third head talk to other people's third heads. Okay, so a person's first head does not talk to other people's second head. Okay, so a person's J's head can only talk to other people's J's head based on this query and the key mechanism. Okay, and then you decide how much you want to make the change. So each head decide how much it want to make the change, and then in the end, we can concatenate the intended change for all the heads. For example, 8 heads. If we have 8 heads, we have 8 delta M. We just concatenate them into a big vector, and again we multiply this by a learnable matrix, and then we add on the existing HM to update it to this new HM. So this is multi-head mechanism. Sometimes we do need multiple heads to collect different aspects for the context. For example, the World Bank. If you look at this should be, I'm sorry, this should be river, not power. So river, if you, this bank, if it's about the river, one head may be about the river or water, and the other head may be about money, right? So it may have different meaning, and you collect each head is collecting information for a certain aspect, a certain semantic dimension. Okay, so that's the idea of a multi-head. So this is one thing that we need to add. And another thing we want to add is this initial for this position encoding. So now with this transformer architecture, so far we don't care about the order. So if we have an input sentence, say I love machine learning, but how about you say learning machine love I? So if you just shuffle the order of the words, you get the same type of computation, right? Because you don't care about the order. But actually the order for the words in a sentence is quite important. So therefore, in the initial embedding, we also add a position embedding so that the summation actually carry the position information. For the position embedding, we can learn a position embedding, say a vector representation for position 1, vector representation for position 2, and so on. But we can also design a embedding so that each element is like a sign. So for the P sub M, M's position, so each element is a sign. This S element may be sign WI, omega I M, or cosine omega I M, where this omega is a frequency. So we may have high frequency and low frequency waves. So this actually similar to the Fourier transform. Those are the Fourier basis. So this gave us position embedding, so that now each word, after you add this two, then each word also carry its position information. And then you can go over this multi-head self-attention to make the update. Okay, so this is the encoding part. So that say I love machine learning, we have 4 vectors, right? Initial embedding with a position information added, and then after this self-attention and add, so residual, right? Add and layer normalization, and then feed forward network and add normalization. So after several rounds, for example, 6 layers, we then have 4 vectors. I love machine learning, but they are fully contextualized. And then we let these 4 vectors to be the input to the decoder. We start to decode the Spanish words, say amo, the first word. We start from start, right? And then we decode amo. And then we input amo to the next step. And then we decode this machinus, right? Machinus. And then machinus next step, we decode the, and then the next to the next step, we decode this aprendido, right? Dido. Sorry to the Spanish speakers if my pronunciation is horrible. I will learn some Spanish hopefully in the future. Okay, so this is the decoder, but in the decoder, you can only generate the words one by one. You generate, you start from the start symbol, right? You generate amo first, and then machinus, and then the, and then aprendido, and then end of sentence, and then you stop. So this is done sequentially. Unlike this transformer where you can parallelize it, here you have to do it sequentially. And when you do this type of sequential generation, so for example, when you generate, when you get to this machinus, right? So you pay attention to the previous words, amo, amo, yeah, you pay attention to the previous words. So this is called masked attention. This is on the Spanish side. You do this self-attention, but you don't pay attention to the words you haven't generated. For example, machinus cannot pay attention to the and aprendido. So you cannot pay attention to the words you haven't generated. You can only pay attention to the previous words, Spanish words. Okay, so this is, again, you have this encoder, you have this one hot vector, and you have the encoder, and then you have the Spanish, the encoding, initial embedding of the Spanish words. You pay attention, and then you mask the future, like time steps, because you haven't generated those words. It's just like you set the affinity to a negative infinity, your affinity score to negative infinity, right? So in the softmax, so that you only assign non-zero attention to the previous Spanish words that you have generated. And again, you use the residual operation and the layer normalization. Okay, and then you each time you just update this single vector, fixing all the previous vectors. You update this vector. For example, the machinus, the vector that's supposedly to generate machinus, right? And then this vector start to pay attention to the vectors produced by the encoder, the final round of the encoder. That's a cross attention. You pay attention to the encoder, the English vectors. I love machine learning, right? Finally, you have the vectors, 4 vectors for these 4 words after n rounds of this self-attention blocks. And then you do this cross attention. You pay attention to the English vectors, and then again add and the layer normalization. And then you do this, you go home. It's like this vector for supposedly generated machinus, then start to do this feed forward neural network, and again add a normalization, and then you get this vector, and this vector can then you go through a decoding matrix, right? And then this vector can generate a logit score for all for each word, so that you have a 6,000 dimensional vector of logit scores, and then softmax to get the 6,000 dimensional probability vector, and then you can decode the word by either choosing the word with maximum probability or sample from this probability distribution over 6,000 words. And then you let this to be the input for you to generate the next word. So this part is, again, autoregressive. You generate word one by one. So each word, for example, machinist, depends on the previous words as well as the input sentence. Okay, so this is a decoder, and you can see that we just change the two boxes, encoder and decoder, from our STM to this self-attention mechanism. And this allows us to do the machine translation in a very accurate way. Again, you may have multiple layers for this box. I use a multiple times n by this n layers or n boxes. So each layer has its own size of weight matrices for query, key, and value of multiple heads. Okay, so that's the basic idea of this transformer. Transformer actually means translation. It has an encoder and a decoder. So again, just to mention a little bit, for the decoding, when we generate this word, right? When we generate this word, we first pay attention to the previous tokens, previous words, and then we pay attention to the input vectors produced by the encoder, and then we do this feed forward network that is thinking for itself, and then we use a decoder matrix to get the logit scores, and then softmax to probabilities, and then we generate the word the. So here, mask means that we don't pay attention to the future words that we haven't generated. So therefore, this model is a auto-regressive model. And ever since the paper on transformer, the attention is all you need, was published in 2017, it quickly dominates natural language processing. So almost every paper adopt this architecture. And in particular, people apply this self-attention mechanism, this type of neural network, which we may call transformer neural network, not only to machine translation, but just to natural language processing in general. For example, suppose we just focus on English. Okay, there's no translation to Spanish or other language. And then we can, for example, train a decoder. We can train a decoder. Suppose that we have the input to the decoder as say the first say 1,000 words. I give you 1,000 words, previous 1,000 words, or maybe say 200 words, the previous 200 words, and then I want you to predict the next word using this decoder, which is autoregressive structure, right? So that is, we don't have the encoder, we only have the decoder. And suppose that you already have 200 words. Okay, you have already generated 200 words, and now I want you to generate the next word based on the previous 200 words. So this is like a prompt. I give you a prompt, and you generate the next word. Okay, yeah, here. So so that's the decoder part, right? Decoder part, and then you just use masked attention. You pay attention to previous word, that is this vector. This vector collect information from the vectors for the previous words at each layer, and then you only have this mask attention. You don't have this cross attention because you don't have the decoder, and then you still add this feed-forward network, and then add layer normalization. So this vector then think for itself, and then this vector start to generate the word after this decoding to get the logic scores for all the words, and then softmax to probabilities, right? So you can just train a very simple model, right? So I give you the previous 200 words. I ask you to generate the next word. And you can make the model bigger, say the previous 1,000 word, and then I ask you to generate the next word. That appear to be very simple, but supposedly, if you train a big model, for example, you have 64 rounds of self-attention. Each round has its own set of W parameters, weight matrices. Then you can train a very big model to predict the next word given what is called a prompt of the previous words. So this is autoregressive model. And the first model that is trained this way is that is only decoder, not encoder. It's called the generative pre-training. So that is, you train such a model over all the documents, all the books, all the web pages you can collect. So there's a huge amount of text data, so that when you do this mini batch training, you only go over each like a text just once. That's enough to train the model. And so GPT means, as I said, generative pre-training. So you train this network in a generative way because you keep generating the next word, and then you use those words, you generate next word. You keep doing that, right? And then you generate a whole sentence. If you give me a prompt, I can generate a whole paragraph or whole article for you. So that's the GPT. This initially was used for pre-training. That's why it's called generative pre-training. Generative means that it is autoregressive, keep generating the next word, and so that eventually you generate a paragraph or an article. Pre-training means that, and then you learn to how to encode each word into a vector, right? So this vector carry a lot of meaning, can be used for downstream task. For example, semantic analysis, whether this sentence is positive or not. This will be just a binary classification. So after you train a model, and you can use this trained model to compute the vector for each word by contextualizing this word from the previous words in the prompt or in the context. And you can use that for downstream task, other like a natural language processing task. Okay, so that's why it's called GPT. And the current version is GPT-3. I don't know whether they are going to have GPT-4, but this version is already quite big. It has 170 billion parameters, very big model. And but now those big companies, they just outdo each other. So the Google recently trained a PaLM pathway language model with supposedly or allegedly 540 billion, half trillion parameters, even a bigger model. And in fact, predicting the next word based on the previous words was studied in the seminal paper for information theory. So this paper already studied this this issue. Shannon's this paper called information theory. This foundation paper, I think it's 1948. Yeah, they show that by learning a statistical model, you can generate the sequence like a sentence. But at that time, of course, the model is very simple, so you don't have very meaningful sentences. But now with such a bigger model, you can generate a very coherent paragraph, because this model has seen all the texts, all the books, all the documents, all the web pages generated by human beings, right? So that's a lot of work. It is, you cannot say this is unsupervised. It is actually a supervision, because all those texts are generated by humans who think very carefully, right? They carry all those complex thought and thought patterns. And then interestingly, by learning this model, you actually can gain a lot of knowledge because, as I said, all those text, the huge amount of text, they actually contain first a lot of knowledge. Okay, so all those facts, for example, what's the capital for US, right? Those type of facts. And it also, because it's trained on Wikipedia, and it also captures this reasoning implicitly, the thinking pattern. So how do we think through a math problem or a logical problem? How do we think about it? So this multi-hop reasoning, right? Multi-round for reasoning. And it also, see those texts that consists of the so-called few-shot learning. So that is, you give some demonstrations of a task, and then you ask question, and you want the answer, you can give the answer. So this type of pattern. So the idea is that by learning this simple model, predicting the next word given previous words, you pretty much absorb almost all the knowledge from the books, and also the thinking pattern, the how you do the logic or how you do arithmetic. So all those things. That is this simple model is simple but scalable, right? Because you can use this simple model and use a lot of heads, a lot of rounds for self-attention, so that you need hundreds of billions of parameters to parameterize this model. And for this prediction problem, the prediction is very simple. It just predicts the next word. But in order to predict the word with accuracy, as accurate as a human being, you have to have the knowledge and the thinking ability as a human being, right? So therefore, implicitly, it learns all the knowledge and all the thinking, logical reasoning ability for a human being. It is very much like what I would like to call a super parrot. This is super parrot. Okay, so here you can actually see. So you keep generating the word by this decoder. So it's like a super, not a parrot, it's a super parrot. You know, the parrot, a bird, right, can mimic human like speaking. And here we train this super parrot so that it can predict the next word as accurate as a human being. Then it must learn the knowledge or thinking ability of a human person, right? So that's the basic rationale for training this type of model. And indeed, this model seems to really have a lot of capabilities. For example, it can solve those tasks if you give some demonstrations, and then it just again, without changing the parameters, it knows how to solve the task, because when it learns from the text, it may see this type of pattern. For example, when a parent use examples to teach the child to solve some tasks, or a teacher use some examples to teach the student to solve some tasks. So it already seen these things from the text, for example, a novel or some books or whatever. So it has this ability. In fact, all the abilities that humans need to predict the next word can be somehow implicitly learned by this model, this decoder model, autoregressive generative model. Okay, so that's the this type of GPT model, and more recently, people also include the image in the loop, so that you can see the image and ask questions, say whether this what this image about. This is a flamingo, and where it come from, or where does it exist? This type of things, these questions it can answer. Yeah, this is a recent like work from DeepMind called Flamingo. It can do this so-called VQ, the visual question answer, VQA. And then they also train this Gato generalized like agent. So it learned from the trained experts, so that it not only answer questions but also can take actions. For example, performing playing the Atari game and so on. So yeah, it can do a lot of things, and people also discover this so-called scaling law, so that if you increase, because you have really a big data of text, right? So you don't need to, you can only go over each text only once, each training example only once. So the data is big enough. And then if you increase the size of the model, that is the number of parameters, you will see a steady increase of the performance. There's a log linear relationship, a power law. So very steady increase in the performance. So almost no limit in sight, as long as you increase the number of parameters. And also, you can also increase the amount of training, the number of epoch that you train this neural network. Suppose you don't decay the learning rate too much. And this way, you can actually keep increasing the performance of the model by making the model bigger and bigger and train the model longer and longer. There doesn't seem to be the issue of saturation. You don't see the saturation or plateau. So you just see the steady increase in the performance in a so-called power law or log linear type of relationship. So therefore, you can pretty much predict the research progress for the next few years, very much like the Moore's law, right, for the computer chips. And also here, when you ask the GPT to perform some task, so you can put some demonstrations in the prompt, right? But you can also just write the prompt in different way in order to improve the performance of the answer or quality of the answer. This may be also the same for human, right? So we use different wordings, and then people may react in a different way. For example, if you be very positive and encouraging, then your student may actually work harder or respond more positively. Or sometimes maybe if you are very mean, then people may respond also in a different way. For example, in a recent example, so suppose you gave this system, you ask the system to solve a very complicated, very complex, difficult reasoning problem. So you keep reasoning, doing multiple rounds of reasoning problem. And if you just ask the GPT-3 to solve this problem, the performance quality, the quality of the answer is not very good. For example, only 17% correct. But if you add this sentence, say, let's think step by step, then suddenly the performance jump to 70%, more than 70%. So that's an amazing jump. So which means GPT may have seen a lot of training examples where there's like a wording, think in steps, or let's split into steps. And then you see what follows is a step-by-step reasoning. So it doesn't get into this pattern, generate the reasoning steps, and finally the correct answer. So this is called prompt engineering, which actually may be just another version of feature engineering. So in any case, I don't know whether you consider this to be a real intelligence. For example, think about the bird, parrot. Parrot can mimic human speaking, and a super parrot may predict the next word as well as a human, as accurate as a human. But does the parrot really has the intelligence of human? And what do we mean by understanding, right? You can think about this. And also think about the parrot. If the parrot need to find food, for example, get the cookie or the meat outside, out of the box, out of a box using those tools, just like a raven, right? A crow, another bird for similar intelligence as a parrot can do. And then this parrot need to do some planning. Okay, do some planning with some representation of the underlying state and the goal. So that may be more about the intelligence, so that you really need to have a very sharp, concise representation of the underlying state and the goal, and then you plan the sequence of actions. So in this way, also, the parrot really may not have enough training examples to mimic, to learn, right? So then you may need a better model. So here there's the issue of data efficiency, whether you can learn from relatively small data instead of learn from all the books, all the web pages, all the documents you can find. So therefore, the intelligence or understanding or knowledge, sometimes they have different meanings. For example, our brain's knowledge may also be inadequate compared to science. That's why we weight Newton, right? Before Newton, when people study the motion of the planet, they use this so-called epicycle, so cycle on top of cycle, this model, and then you need a lot of parameters to fit the trajectory of the planet. But later, Newton, after this Kepler, discovered that actually the motion of the planets can be described by a very simple physical laws that can generalize from the falling apple to the orbiting moon, right? So it has a bigger generalization and a simpler model. So therefore, when we talk about understanding, we have to, it's just a matter of a continuous spectrum for different model complexities. So a very complex model may not be data efficient and may not be concise, parsimonious enough, but it still account for a certain understanding. Just like we cannot say like this epicycle model is wrong, or Newton's model is correct. And Newton's model is also wrong compared to Einstein's general relativity, right? So therefore, different models, they serve for different purposes. They are all useful in different scenarios. So therefore, we can also say that the GPT also gains some knowledge and understanding and the ability to do reasoning, even though it may not be as data efficient or as explicit as human reasoning. In fact, what we mean by explicit is also, or interpretable, is also subject to debate. So this is a decoder part. And after GPT was trained, people also developed this BERT, bidirectional, this encoder representation, embedding representation through transformer, whatever, BERT. This BERT is based on this bidirectional, so it's not generative. It's really just take this encoder architecture, okay? And then again, for the English text, it doesn't seek to generate the sequence for words. In fact, for each sentence, each paragraph, whatever, it removes or randomly masks 15% for the words. And then they use this encoder, a bottom-up encoder, to encode all those words, including the mask word. For the mask word, you start from this mask symbol, and then you contextualize them. So this mask symbol keep collecting information from other observed unmasked words, so that eventually it collects enough information so that it can predict what's a word being masked. So this way, you just, it's called self-supervised learning. You mask some words from this sentence, and then you try to predict the masked words. This way, you can learn a encoder. So this is the BERT, only using the encoder part. And then you can train to encode the words, contextualize the words, so that this embedding or the encoding can be used for downstream task. And when you do that, because the encoder is bidirectional, right? Unlike the decoder with this mask attention, you can only attend to the previously generated words. So here you can attend in both directions to this bidirectional. So this BERT embedding is very useful for this word vect So you start from the word-to-word initial embedding and you contextualize. You learn to contextualize so that you have the final embedding, which can then be used for downstream task. And this BERT embedding is now very commonly used in natural language processing. Okay, so just to summarize, the original transformer, which is all based on attention, has an encoder and a decoder from one language to another language. But then GPT take the decoder part to predict the next word based on the previous words. And the BERT take the encoder part to encode the words into the vectors, contextualized vectors for downstream task. This pretty much what I have for this this lecture, and it's quite interesting. I think maybe you can find the original papers and follow the more recent progress. But I think we can predict that the model will get bigger and bigger, and the compute will also become more longer and longer, and then you train a better and better model. So for the next maybe 1 or 2 years, that's what we can predict. Yeah, so maybe I can stop here. Thank you for your attention.